Hi, and welcome back to Codex. Our speaker today is Raj Rao from the University of Michigan. He's an expert in statistical signal processing and applications of random matrix theory. Today, he'll tell us about a special application of matrix completion. Take it away, Raj.
Great. Thanks, Emily and Dustin. It was nice to meet you all for the first time, I think almost a month ago, and it's nice to see you all in person, including Doug's cat. So thank you again for inviting me and for letting me talk about this stuff. Before we start, I wanted to highlight a little bit of the portion of the title that perhaps you're wondering about, and maybe an invitation for you as I go through the slides, if you would, is to try to anticipate, what might I mean by an asymmetric SVD, right? Obviously, I don't mean it like an SVD of a rectangular matrix, like a linear algebra student who's still on the learning edge of the curve, but it's something that perhaps you might try to anticipate before I actually get to it. So as a way to preview why that object, if you would, came up in what we were trying to study, let me set up the problem, which is the very sparse matrix completion problem. So here's a couple of notation that'll pop up throughout the talk. What we have in mind here is a low rank matrix A that has a known, for now, assumed rank R, and it's expressed via its singular value decomposition as just this summation from I equals 1 through R, sigma I, Ui, Vi Hermitian. So the Ui's and the Vi's are the latent left and right singular vectors, and the goal is to reconstruct this matrix from an input given by A tilde. So A tilde is the matrix A observed in a very sparse manner. And the way it's observed is essentially we see the matrix entries Aij with probability P, or we don't see it, or in effect, it's as though there's a 0 or a question mark with probability 1 minus P. So from the perspective of this problem, our goal is given as an input to the algorithm, the A tilde matrix, and let's say then rank assumed known rank R, we want to reconstruct as accurately as possible the original latent low rank matrix. So the particular problem we have in mind deals with a situation where the knob, if you would, which is the probability of observing the entry, in our situation is given by this D over N. We'll talk about different regimes of this value of P, but what I want to emphasize is that D over N is a really sparse setup, which means that we are on average, if the matrix size is N by N, we're roughly observing about D rows per row or D rows per column. Okay, and why is that really sparse, and why is it sort of more interesting? It's really, if you think of where these problems come up, one of the prototypical applications is something like matrix completion for the Netflix problem, where you have as rows the users, the columns are movies, and every time, let's say, a user watches a movie and rates it, maybe they're filling in their rating of it on a scale of long time back 1 to 5, and these days +1, -1, at least on the Netflix system. So you can imagine when the number of movies keeps increasing, it's not like folks are reviewing more and more, right? So in a lot of the classical literature on matrix completion, one talks about the situation where D is roughly log N, which works well for theory, but in practice, it's hard to imagine that, let's just say, at least I'm not catching up with Netflix the way it's, churning out movies or serials. So roughly on average, the number of movies a user is watching and rating is constant, is a more interesting practical regime than assuming that the users are catching up with the rate of growth of the movies, so to speak. So that's really why extreme sparsity is important and interesting, and that's where we want to focus our theory and also prospective algorithm. I want to give you a little bit of a sense of when matrix completion is easy and when it's difficult, and just to set up the role of the structure in the singular vectors in terms of how we can think about this problem. So here's a simple example. If I told you that A1 tilde was this matrix 1, 2, question mark 4, and if I didn't tell you that it was low rank, of course, this question mark could be anything, right? It could be 0 if one wanted a minimum Frobenius norm type of solution. It could be infinity if we put no constraints. But the moment you say it's rank 1, it's obvious it has to be 2, and it's unique just because it means that the first column has to be a multiple of the second column. The converse side of it, which brings into focus the structure and the singular vectors of the matrix, is illustrated by this particular matrix at the bottom, which is A is equal to 1, 0, 0, 0, or effectively E1 0 or not 0 transpose, but E1 transpose. And in this context, what you can see is that if I were to randomly select an element of that matrix, then there is a non-zero probability, specifically corresponding to if the top left entry was obscured, where I might not ever be able to reconstruct that matrix with zero error, so to speak, right? So the game we're playing is there's some randomness in terms of how we're sampling the matrix. We'd like an algorithm that reconstruct that matrix with very high probability. In situations like this counterexample, where you get this extreme element-wise sparsity, it's not possible to do that because if you drop those very large entries in some way, then there's a constant probability that you just might not be able to reconstruct that matrix. Okay, so this is at some level at a higher level boiled into the so-called delocalization assumption, which is that the matrices we're looking at have singular vectors that are, if you would, spread out or incoherent. And an example of an incoherent matrix is one where the singular vectors are, let's say, all roughly 1 over square root of n. The contrast to that is a matrix that's coherent, if you would, or singular vectors that are localized, which is something of the form in the counterclaim that I talked about, right? So a matrix that has, let's say, sparse entries has localization, and that's a situation where we don't expect matrix completion to generically work. But everything we're doing here, we're placing ourselves in a situation where the matrix is incoherent by design, and we want to see how well does the algorithm do. And we want an algorithm that with very high probability succeeds regardless of the random masking pattern. So a couple of quick bookkeeping points, which is when we think about that matrix and we're looking at the entries with probability d over n, this slide is going through the purposes. What should d roughly be so that we feel like the matrix reconstruction problem is easy, difficult, or impossible, or maybe even challenging. So we can quickly get a sense of it in a back of an envelope kind of sense by just counting the number of parameters that are in the matrix, regardless of how it's arranged, or regardless of what algorithm might actually extract the information we're chasing. So roughly speaking, if we have this m by n matrix with incoherent singular vectors and a rank of r, then on the roughly speaking, the number of parameters we have that need to be estimated are about order r of m, right? Which is much less than the total number of entries in the matrix, and that's what gives us hope. If we observe each element of that matrix with probability d over n, then roughly speaking, for this m by n matrix, we have about d times m different entries. So you can kind of see why the d equal to order n, which means that probability of observing an entry of being order 1 is relatively easy, because roughly speaking, the number of elements that are observed are much bigger than the number of free parameters. So, without worrying too much about what that algorithm might be, you might imagine that solving that nonlinear system of equations should be, in principle, not too difficult. Okay? And that turns out to be the case, and we'll illustrate what happens with some simple algorithms. In contrast to that, if you have d to be roughly order r log n, or p is going to 0, but sort of has this numerator that's r log n divided by n, then you might imagine, based on this argument, that, okay, we have slightly more elements that are observed by a factor of log n relative to the number of free parameters, so we should be able to do it. But of course, you're getting to the edge of difficulty, so to speak. And of course, the part that gets more interesting is when the number of parameters does exactly, if you would, match the number of elements observed. And in this context, that's the very sparse matrix completion problem, where d, which is the average number of entries revealed per row or column, is on the order of the rank of the matrix. And that corresponds to exactly the regime we're putting ourselves in, which is p is roughly d over n. Okay, so the purpose is to give you a feeling that the first two we hope to be easy. Perhaps we expect perfect reconstruction. The third one, we don't expect perfect reconstruction because we really are right on the order of the parameter count. Okay, so let me show you with some numerical experiments what happens in terms of the reconstruction as you vary stuff, but also to give you a little bit of a peek on what's happening under the hood in the mathematics, particularly the mathematics of the random matrix that's associated with this random masking pattern, if you would. And I'll begin that story, if you would, with this simple example. So here's a logo of MIT. You view it as a matrix of grayscale values. It's actually a rank 4 matrix. It's kind of a fun linear algebra exercise for students to count out the columns that are independent. If, as a thought experiment, before we go into the full random matrix model or the random masking model, I were to tell you that I removed just a single pixel in this entry, and then I were to use a truncated SVD to form an approximation of the matrix, I think you'd believe me, or you can see this. You can see the origin of the idea that matrix completion should be straightforward, because if I remove just one single entry, and if each of the singular vectors were delocalized, which means they're all roughly 1 over square root of n, then that single entry is on the order of roughly 1 over n. So deleting a single entry of the matrix doesn't really change. It's basically as though you're perturbing that matrix with a small error, which is on the order of 1 over n. So the singular vectors are pretty much of that truncated SVD with that missing entry, so to speak, replaced by 0, are already pretty close to the original matrix. So we expect with some, hopefully, magic, if n is big enough, to be able to reconstruct that matrix by starting with an approximant that's really close to the original one that we're seeking in the first place. Right? So the perspective here is the same idea that a single entry doesn't change the norm or the perturbation of the matrix too much is really the idea behind when the matrix completion problem is easy. And the starting point of that is replacing the matrix with missing entries with all zeros where the entries are not observed, taking the truncated SVD, and then seeing what happens as we iterate the algorithm from that. Okay, so here's an example which is a bit more extreme compared to the situation where we removed a single pixel. So what I've done here is I've taken the MIT logo. This is that rank 4 matrix, and I've put about 70% of the entries are observed. The ones that are deleted, if you would, correspond to the dots you see, the black dots. So here we want to just get a feeling for, okay, how do we think about the system and what's going to happen in terms of matrix completion? Okay, so what I did in this simulation was I took all of the entries that were not observed and replaced them exactly with zeros, did the rank 4 truncated SVD, and what's plotted on this slide is the rank 4 SVD of that matrix with zeros, whatever the entries were not observed. So what you notice is the error with respect to the original matrix is about 0.305. It's not perfect. It's far from perfect, but actually it contains a lot of the interesting information we expect to see in that MIT logo from the ground truth point of view, right? You certainly see it really does look like a rank 4. You see all of the stripes of the MIT logo, but of course you see some other artifacts which we'd like to, of course, get rid of. So here's a proto algorithm that I want to describe that I think will give you a feeling of why the first step of the SVD is really important to understanding how and when and if matrix completion will succeed with more complicated algorithms that try to get rid of this aliasing artifact, if you would, that appears in step number 1. Okay, so what I've done here is in this rank 4 SVD, you notice this weird stuff pops up. In second step, what I can do is I can replace the parts of the matrix with the entries that I know to be correct and do another truncated SVD. So it's almost like an alternating projection algorithm. And then I can keep repeating that procedure by utilizing the information of the entries that were revealed that I know to be perfect. And if I do that, what happens is in the second step, the error starts going down from 0.3 to 0.11. If I repeat that process again, so the parts of the matrix that were revealed, I replace it with the correct values, I do another SVD to it, and then I keep going. You'll notice at every step, it keeps getting better and better, and eventually the error goes down to 0. Okay, so if I look at the inner product of the, let's say the left singular vectors as a function of iteration, you notice that in step 1, it's not very good, but it's not bad, right? And that's really the key to what we're building towards, which is it's important that the SVD of the matrix in step 1, where you replace the entries with 0, contains something. If it contains something, then using the information that's perfect in a belief propagation-like way, so to speak, informally speaking, you can keep improving that estimate of the singular vector until it eventually is almost perfect. So some noisy information in step 1 gives you hope. We'd like to understand when does hope break down, so to speak. And perhaps based on what I've shown you, you might wonder whether something is possible when there is no hope in step one, which is when the singular vectors are completely junk, so to speak. Okay, so that's what we're working towards in the next few slides. So what happens if we make this even sparser, right? If we repeat that same process, if we make P to be 0.5, so about half the entries are revealed. In step one, it's again not very good. It kind of has an error of 0.5. But if I keep repeating it, eventually it kind of stagnates at this point, right? So it's not great, but eventually it'll keep getting better. But in step one, you notice there's some error, but most of the information of the MIT logo is sort of there, even if it's noisy. If I make it even sparser, so if I observe only 20%, then you notice this phase transition-like effect, which is some parts of that MIT logo now are disappearing, right? So for example, the portion that's corresponding to the middle of the M seems to have been lost, right? It seems to be replaced with the solid column going all the way through. It looks like the dot on top of the I is also disappearing. So some of that subspace information seems to be lost, or at least one wonders if it's recoverable in any way. But nonetheless, there's some information, even if it's not perfect. And the information that is there seems to be incoherent in the sense that it's spread out across the columns and the rows, right? No particular row or column dominates in a way that we'll want to keep interrogating as we lower the sparsity further. Okay, so here is the extreme case, right? This is the regime we want to work in. This is the regime where I only observe 1% sparsity or 1% of the entries. You notice I'm barely seeing anything. This is kind of like a low light imaging type of setup. And now in step one, if I replace the rest of the matrix with zeros and I compute the SVD, you notice that I really am in trouble. I really don't even see anything about the MIT. My brain right now is hallucinating some bars just from looking at the previous ones, but there really isn't much, and the error reflects that. Okay, so before I go on, let me just zoom in a bit more. And what you'll notice, if I zoom in just a little bit to give you a feeling on what's happening, is that the singular vectors are not obviously all zero, right? Obviously, singular vectors have to have norm one. They're normalized in that way. But what you notice when you zoom in, the spectral forensics kind of tell you that the singular vectors that are obtained by the SVD in step one are localized in a way that the original singular vectors are not, right? So that's giveaway number one, that something's happening in the singular value decomposition at that very sparse random matrix limit that's breaking down the structure of the singular vectors. If the singular value decomposition was doing the right thing, we would expect delocalized vectors to show up as delocalized vectors, but somehow it's doing in some weird distorted way of filtering or distortion of the phenomena, so that delocalized vectors via this random missing are popping up as localized vectors. Okay, so that's bad syndrome number one, in a way that is not salvageable regardless of how many steps we do. And this is where we want to work in, because it looks like maybe there is no hope for the SVD to do anything. Okay, so let me summarize what we've seen so far to set up the problem and maybe have you wonder also what exactly this asymmetric SVD I'm talking about and where it might have come up. Right? So on the left-hand side, I'm showing another example of a rank 1 matrix. If you observe it in that very sparse limit, and if you reconstruct it with the SVD in step number one, you really will get in the large matrix limit a normalized mean squared error of 1, indicating that it's basically as though it's a matrix of all zeros. So the SVD seems to break really badly. However, if you were to have D to be order log n, that's the regime of classical matrix completion, there everything works out well and you get perfect reconstruction. So the perspective here is when the SVD breaks down completely, the singular vectors are localized the way I showed you, and that appears to be below what folks referred to as the information theory limit of reconstruction. And one might wonder, can I recover information in this regime where that first step of the SVD, which is also the first step of a nuclear norm-based reconstruction and all of the allied schemes that use spectral information, is it possible to salvage something? Okay, that's really the setup that we're working on. And the affirmative answer, of course, is yes. The story I want to lead you through a little bit is what is the chain of thought, if you would, that led to this new algorithm beyond just, of course, the details of that algorithm. Okay, so let me give you a bit of a preview of how we might think about this problem as a starting point for imagining a different algorithm that has flavors of a spectral method, but somehow overcomes the limitations of the SVD that we've seen using some of the diagnostic tools of random matrix theory. Okay, so here's kind of the way I think about it. If we want to use random matrix theory to reason about how easy or difficult the matrix completion problem is, then it's helpful to get a perspective for why should this algorithm even succeed in the first place. And a straightforward way of thinking about that is to view it almost via the lens of perturbation theory, if you would. So if I were to look at the matrix A, or the observed matrix A, which has each element observed with probability P, then really we can take the expectation of that matrix and we can write it as a perturbation where we decompose that observed matrix A tilde as expectation of A, plus basically a perturbation about its expectation, if you would. So the way I'm writing it here is it's roughly P times A plus delta. Now, really what I meant, there's a small typo here, is it should be P times delta because I want to absorb that P into the delta and have delta just reflect that composite normalized perturbation. So just from a linear algebra 101 perspective, you might imagine that, okay, if I wrote this as PA plus P delta, then the error in the singular vectors of that low rank matrix A, aside from that scaling part of it, really are governed by the spectral norm or the operator norm of that delta matrix. If the norm of that delta matrix is going down to 0 as n goes to infinity, then we expect perfect reconstruction, and that's exactly what happens. So it turns out that if D, which is that average number of rows or columns you observed, is roughly n log n, or r log n in that context, then we do get exactly that, which is the sigma 1 of delta, which is that the spectral norm or the operator norm of that perturbation really goes down to 0. And then it makes sense that, okay, if the norm is going down to 0, step number 1 is sort of very close. And then with some other convexity type arguments, we can eventually kind of drive it down exactly to 0. The problem really happens if sigma 1 is roughly on order 1, then I think from linear algebra perspective, we already have a feeling that, okay, we're in a little bit of a trouble. We can't expect perfect reconstruction because if both norms are roughly the same, how can we expect to overcome that? And of course, if we're in a setting where sigma 1 of delta is going to infinity, then of course we're even more worried because then the noise, if you were just swamping the signal, the P times A singular vectors, and then we really don't expect to get anything. So from the perspective of the simulations I showed you, when enough entries are observed, we're in the perfect reconstruction setting where sigma 1 delta really does go down to 0 if you scale the matrix the right way. When we're in the very sparse regime, it really does turn out that sigma 1 of delta, from the point of view of the situation where P is D over N, goes to infinity. It goes roughly like log N or square root of log N. And that's the situation where we're in trouble, where the singular vectors of the SVD become localized as opposed to delocalized. And it seems like there really is no spectral way to overcome that barrier. Even though from a parameter counting point of view, it seems like we're roughly on the order where we would hope to get noisy recovery, if not, but even as we don't expect perfect recovery. Okay, so just to kind of recap, the situation we have in mind is where we have the sparse matrix with the masking matrix. And the basic idea is that even if we use nuclear norm methods, alternating minimization, if that step 1 of the SVD corresponding to where sigma 1 delta is going to infinity, we really are in trouble, and all of these methods inherit the flaws of the first step basically being broken irretrievably. Okay, so what I want to talk about is in that same setup where we have a low rank matrix, and in that seemingly impossible for the SVD regime, where the average number of entries is D, and D is order 1, so we really don't let it grow. Is it possible to reconstruct reliably with some error, even though it's not perfect? Are there polynomial time algorithms that are relatively straightforward to implement? And what are the limits, if you would, of reliable reconstruction in that regime? Okay, so the good news is we can do all of these, right? So we can reconstruct. There is a simple spectral algorithm, which I've hinted at, which is what is that asymmetric SVD? Maybe you're pondering and wondering what I mean by that. And then there are two different types of limits, or really three different limits based on different variants of how we play with the data. Okay, so let me show you at least the results of what happened, just to show you that it really does do something non-trivial. So the left-hand side was the situation corresponding to the true rank 1 matrix. The SVD really fails horribly. It gives basically almost a junk as a reconstruction. And now there are two different methods I'll talk to you about. I'll focus more on the third column, which is what we're referring to as the asymmetrized SVD, which in that regime that's very sparse, gives you an estimate that's pretty good, right? So it's not perfect. It has a normalized mean squared error of 0.5, but it does way better than what the SVD does. And there's another method which is even more computationally intensive, but also has a spectral flavor to it that reduces the mean squared error by about 30% more, and that's what we refer to as this WNB SVD. Okay, so in the rest of the talk, I want to give you a little bit of a flavor of what these algorithms are, motivated by, I hope, your curiosity, just that what exactly are these doing that the SVD is not able to do, and how did we stumble upon these algorithms in terms of the diagnostics of random matrix theory that led to our thinking that it was even possible to do this in the first place. Okay, so those are those two algorithms, those are those two different limits, and those are the ones that we can kind of do. Okay, so let me tell you the core idea by switching the problem to a closely related problem, which is not the SVD problem, but the matrix completion problem in the symmetric setting. Okay, so here what I have in mind is just like the SVD problem, but now we're switching to the symmetric setup. We have a rank 1 symmetric matrix. So I equals 1 through R, lambda I, UI transpose, right? It doesn't matter if it's complex. And now we're looking at this matrix here. The point is, we have this matrix again with the symmetric mass. So M is that masking matrix, and it obeys the symmetry constraints the way it would have for the SVD, except now it's symmetric. So it's a symmetric masking. The same situation that happens in the SVD happens here as well. So it turns out if I were to play the game with D, where D is that average sparsity, this symmetric I would also break down in an equally bad way in the very sparse regime. But here's the key point. What we notice is when it breaks down, you get these localized vectors, and the localized vectors occur because it turns out certain rows and columns of that A matrix are, the degree of that, if you would, is particularly large. And at some high level, when you're computing the eigen decomposition, it's as though you're taking powers of the matrix, so to speak, and it ends up concentrating on the vertices or the rows and columns of the matrix that have unusually large degrees when you view that matrix as a graph. Okay, so with that as a big perspective, what the idea we had, and the real focus of the talk in a bit, is how did we come up with this idea to prove what we did in a robust way, is to take this matrix A and not work with the matrix directly, but to sort of randomly asymmetrize it. Okay, so let me go more methodically here so you can see the origin of the idea. So I have this matrix A that has missing entries. What I do is I take that matrix A and I create a new copy of it, which I might call, let's say, A bar or A tilde bar, by essentially doing the following. If I have a matrix A which has symmetric part, so you can imagine it's got an upper diagonal part and a lower diagonal portion, I flip a coin and I either take for every entry that's revealed, I either take the top part of it or the bottom part of it. Okay, so visually what I have in mind is something like this. I have on the left-hand side the original incomplete symmetric matrix. I'm breaking basically the symmetry by either taking an element on the top or the bottom. Okay, so essentially I'm doing that symmetry breaking and converting a symmetric problem into an asymmetric problem, right? That's the origin of this asymmetric SVD idea, is you break symmetry intentionally, but in a randomized way. If you now compute the eigen decomposition of this randomly asymmetrized matrix, what we were able to prove is above a certain explicit threshold, as in a signal detection threshold, the eigenvectors of this random asymmetric matrix will be reliable estimates of the original low-rank eigenvectors. Moreover, the interesting part, of course, and all along in my education, I was always scared of asymmetric matrices and what do I do with the left or right? Which ones do I play with? It turns out the left and right both contain information. If I were to average the left and right eigenvectors, it turns out they are better estimates of the latent eigenvectors than taking only the left or only the right. As in, they both contain information that's correlated, but they also contain some information that's a little bit independent and noisy, and averaging them does better than just taking one of them. Okay, so this is the construction of that asymmetric eigendecomposition, and maybe you can guess how this goes from the symmetric problem to the SVD, because I'll tell you that in just a bit. Okay, so I want to show you a couple of theory of what happens in this problem, how we can compute the explicit phase transition thresholds in terms of when recovery is possible and when recovery is not. So here's a couple of parameters. It turns out the object that governs, there are two objects that govern basically the location of the phase transition of this matrix completion using this method. One is you take that matrix, the low rank matrix P, you scale it by n, and you compute basically the largest L infinity norm across the rows and columns of it. Okay? That's the amplitude parameter L. You can kind of see if this was a matrix that was not incoherent, L would be infinity, and basically the theory says you can't deconstruct. If P has elements that are on the order of 1 over n, then this just in effect tells you what is the largest column or row of it, and that's just a parameter that comes in. In terms of computing the actual detection threshold of when matrix completion is possible, the object that comes into play is this row parameter, which is in the top box. And that row parameter is basically the spectral norm of the matrix P, element-wise squared, and then rescaled by a value of n. Okay, so there's just a explicit spectral constant that pops up via this row. And then there's another theta parameter that's related to it by doing, this gamma 2 is theta, or this row divided by d. And now here's that final inner product between the true and the estimated eigenvectors with high probability. Okay, so it's a slightly messy looking formula, but I just want to show you that it only depends on something which is governed by basically that spectral radius of that low rank matrix via the, this nu2 parameter, the eigenvalues, and then that's it. Okay, so here are a couple of formulas just to show you what they look like when you sum this out to, large size matrices. It turns out that inner product is governed by basically the kurtosis of the elements of that eigenvector, which is an interesting new feature that's different than the traditional random matrix theory, where the distribution of the elements almost doesn't seem to matter. But here, really explicitly, you get that, the kurtosis of the elements of that eigenvector come into play. And here are a couple of plots just to show you that the theoretical predictions are really very accurate when you run numerical simulations. Okay, so on the left-hand side, I'll just show you what's happening. On the x-axis is D, which is that average sparsity. On the y-axis is the inner product. So this is the inner product between the left singular vector, which is the correct one, and the estimated one using this asymmetric SVD or asymmetric eigen procedure. The solid line is the prediction from the theory. The dots, if you would, are the asymmetric left eigenvector and the asymmetric right eigenvector. You notice they really do overlap. They contain the same inner product. The dashed vertical line is the phase transition, which is, this is the number below which you can't expect to have matrix completion using this asymmetric procedure. And that solid line depends on the kurtosis of the elements. So if I were to populate the matrix with normally distributed entry, that solid line would be at 3. If I were to have, let's say, Bernoulli +1 -1, that solid line would be at 1. So this line really moves around based on how spread out the tails of the elements of that matrix really are. Let me move to the second panel. So in the second panel, what you notice is the red line is the theory for just the left and right eigenvectors. If I were to average them, that's the blue line. And you notice that it doesn't break the phase transition, but the accuracy of the eigenvectors improves. In contrast, you notice the plus is the symmetric eigenvalue stuff. So as in, if I didn't do this asymmetric procedure and use the eigendecomposition, you notice that the eigenvector estimates are substantially worse, particularly in the very sparse regime. If D is big enough, then eventually the symmetric routines gives you as informative estimates as the asymmetric procedure, but the real value is in the regime where here, let's say between 3 and 10, where the symmetric one just doesn't have very good eigenvectors. Let's move to panel number 3. So in panel number 2, it looks like the symmetric eigenvector is not that bad, right? The eigenvector looks like it has an inner product maybe of about 0.5 when D is about 10. The right plot, what it does is it does the L infinity error between the eigenvectors, and you see that the eigenvectors of the symmetric matrix with missing entries are substantially worse than the L infinity norm in a way that the asymmetric ones are not, right? So the inner product doesn't quite capture the extent to which the localization is happening in the symmetric eigenvector case in a way that the third plot captures, right? So you really notice that these asymmetric eigenvectors are much more stable and robust above the phase transition than what the symmetric eigen decomposition method is able to do. Okay, and that's the situation where, again, they're all above that phase transition. The phase transition really depends on the threshold. The threshold is governed by the kurtosis, which for normally distributed entries would be exactly 3. This one just shows you the same phenomena. So on the left-hand side, you see the agreement between theory and practice. I happen to use the hyperbolic secant, which happens to have a kurtosis of 5. So the phase transition moves a bit to the right. Once again, in the second panel, you notice the symmetric eigenvector is much worse here. So that's the interesting insight, which is if you're trying to complete a matrix that has heavier tails as encoded via the kurtosis, the gap between the new method and the symmetric eigenvector-based methods is going to get larger and larger, right? So that's another interesting new phenomena that even we didn't expect when we went through it. And that's a very easy way to induce regimes where matrix completion does even worse using the spectral initialization based on the original SVD. But if you were to use this asymmetric method, then it really is robust throughout that regime. Okay, and the third panel shows that. You can see the L infinity error of the symmetric eigenvector is really bad throughout the range of D until much higher values of D than the normal setting. So these are not exploding kurtoses, if you would, but the kurtosis obviously plays an important role in a way that for other variants of random matrix theory, typically that's not usually the case. Okay, so perhaps you're wondering how we can convert this into the SVD setup and where the asymmetric SVD comes in. And this slide basically captures all of that story, which is, I told you what happens for the symmetric case, which is you intentionally are taking the top and the bottom. The way we get the asymmetric SVD is to really take, for example, on the left-hand side in red, if it was a low rank matrix, I want to convert it, and I'm given this matrix A, which has those missing entries with basically, the usual mask given by M. Then instead of taking the SVD of the matrix A, we instead form a symmetric matrix first, which is 0, A, conjugate Hermitian, and then A 0. And then now you apply the same procedure as before by taking the top and the bottom of it. Okay, so pictorially, this is the way we think of it. Left-hand side was the incomplete rectangular low-rank matrix. We first embedded into a symmetric matrix because its eigenvectors really are closely related to the the left and right singular vectors of the SVD. Then we do that randomization procedure, take the eigenvectors the way we suggested earlier. We, of course, peel them off to reform the U's and the V's, do the averaging in the way that's suggested, and now you have the SVD via this asymmetric procedure where randomization plays a very important role, but in the ways that we described earlier. So, and that's what gives us this improvement. So the last part of the story I want to focus on is what is the origin of this randomization, and the asymmetric part is how did we, if you would, what facts did we know or build on that gave us a feeling that this procedure could succeed? Because to be honest, it wasn't obvious to us at all, right? But I want to give you a feeling of, how you would have done it too if you had just happened to know the fact that I happened to know at that moment when Charles Bordenoff kind of told me about it, and then the rest sort of came out almost by magic. Okay, so I want to go back to the perturbation theory perspective that I started on earlier in this talk, which is this idea that if I have the observed matrix A and I just expand it, if you would, above its expectation, we can think of it as the expectation of A plus A minus expectation, which is really, I want to write it as PA plus P delta, right? So I think the story, perhaps you believe me, or maybe you can, as a placeholder, just suspend disbelief, which is if sigma 1 of delta is going down to 0, kind of like floating point arithmetic, if you would, then we expect the matrix completion problem to be easy. But if sigma 1 of delta is going to infinity, then we expect that we're in trouble, because what do we do about it, right? And in the situation where the SVD breaks down, it turns out it's exactly true that sigma 1 of delta, which means the largest singular value of that delta matrix, is really going to infinity. So there's really seemingly nothing one can do about it. The trick, of course, is captured in this slide. So I'll just go through it in a couple of different ways. So what happens, what's plotted here are a couple of things. So the solid lines that you see going from top to bottom are just the singular values represented in complex planes, so to speak. So really, we should be thinking of it as the singular values are all positive. So you notice the gray lines are going top to bottom, and the intercept of the solid line with the x-axis represents the locations of the singular values of that delta matrix, or this matrix perturbation 1. What you notice is that there's a lot of lines that are clustered near 0, right? There's a solid band, but there's quite a lot of lines that are spread out. They kind of spread out like fingers, if you would. And that's the phenomena that has to do with the fact that sigma 1 of this delta matrix is really blowing up to infinity. So no matter what you do, the sigma 1 is blowing up. What's plotted in the purple dots, if you would, are the eigenvalues. So the complex eigenvalues of what happens to the delta matrix when you do that masking operation. What you notice that's very different is that these complex eigenvalues are nicely contained in a ball or a circle of exactly that radius given by rho, that detection threshold. But none of these complex eigenvalues, except the 2 of the ones corresponding in this simulation to a rank 2 matrix, bleed out. And that's really the origin of the idea. So it turns out, in these situations, the largest singular value of that delta matrix goes to infinity, but the spectral radius, or the largest eigenvalue of that delta matrix that's masked, turns out to be bounded. And that was, if you would, the idea that led to this algorithm, which is in the singular value domain, everything is blowing up. But somehow, if you do this randomization procedure, the eigenvalues are very regular and they stay nicely compact, if you would, within a very nicely closed form prescribed radius that we can almost analytically compute a priori. Okay, so the insight that's sort of written here is that it turns out that if you look at those masking matrices, for this Erdős-Rényi graph, the undirected Erdős-Rényi operator norm is unbounded, but the directed version of that same thing has spectral radius that's bounded, right? And the moment you know that, then you can kind of see that if in one domain, which is the singular value domain, if things are getting unbounded, we expect things to break down, so that's not a big deal. But the moment we swap it to the spectral complex domain, if the spectral radius is kind of bounded, that embedding is very forgiving, and that's where we can extract information, right? So that's really the idea that led to this algorithm, and then the rest of it is just important, difficult, but inevitable, so to speak, results of the analysis of all of this going right through. Okay, but the idea again is the singular values spread out, the eigenvalues don't. So converting it into the eigendomain sort of lets you pull information in a way that the singular domain doesn't seem to be able to capture. Okay, let me give you one other definition of a matrix. I think I hinted at it, which is the WNB SVD. So it turns out there's another matrix you can form from this matrix called the weighted non-backtracking matrix. It's a matrix that's much bigger. It's a matrix that's roughly of the size, the number of revealed entries by number of revealed entries. It also is asymmetric. And if you compute its eigendecomposition and then somehow recompose the eigenvectors from it, they'll be better than this average SVD because it uses all the information and doesn't drop stuff across the diagonals. So consequently, the threshold of recovery is about 1 over square root 2, lower than whatever you would get using the asymmetric procedure. It's a little bit more involved. It takes a lot more computation, but it essentially utilizes the same idea. This is a bit more obvious to folks who work in graph theory, This is not the way I think of things. The other one was a bit more, it's a simpler algorithm, if you would, for me. So in a lot of ways, it was more satisfying for me to kind of see that a simple one kind of came about. I think for folks who know graph theory, this seems obvious, but it's not obvious to me at all. But it's kind of maybe satisfying that it does a bit better. Okay, so here's a couple of qualitative pictures showing you how that spectrum works. So in both of these simulations, we have a rank 2 latent matrix. On the left-hand side is the spectrum of the asymmetric embedding. You see the circle corresponding to the spread of the noise, if you would, complex eigenvalues. One of the eigenvalues of the latent matrix is below that radius. So this is the eigenvector that would not be reliably estimated because it's below the detection threshold. You might remember in the MIT logo that corresponded to that sparsity level where we dropped the dot over the I. That would correspond to a situation like this. The largest one turns out to be okay, and it flies out from the bulk, so you can estimate it reliably, even if it's not perfect. In this simulation, you notice the asymmetric eigenvalue guy. The second eigenvector cannot be estimated, but if you did this weighted non-backtracking spectrum, the spectrum looks kind of cool, looks like an owl. We don't really know how to characterize that in closed form, but the second one now emerges from the bulk in a way that it didn't when you did the randomized procedure. It's a little bit more costly to evaluate it numerically, but this is the utility of doing that, is you really can squeeze out that last bit of information. Okay, and here are just quantitative plots of the red line was what I showed you earlier. That's the situation corresponding to the, the averaging the left and right eigenvectors. And you notice the blue line is the new weighted non-backtracking stuff. It does better. It has a phase transitions that's lower than the asymmetric procedure. And the L infinity norms are also uniformly better in that case. Okay, so I'll give you a couple of high-level ideas of how the proof kind of works. At some basic level, even though this is a matrix problem, it's more instructive to go through and think of it as a graph problem. And the particular connection here that's taken advantage of in the proof is really in that very sparse limit, viewing it as a diluted tree. And particularly because of that sparsity, it's sort of a rooted Galton-Watson tree. So if you understand the spectrum of these trees, in some sense, you understand that the spectrum is connected to these eigenvectors, and an important identity that shows up is this Hoffman-Wieland identity, which is kind of cool too, because it bounds the, we're often used to the perturbation results that have to do with singular values. This is an identity that has to do with the complex eigenvalues, and that plays an important role in the analysis. My collaborators, Charles and Simon, they really are the experts in this, and I learned a lot from how they do things. Maybe the more natural thing for me to do was to just do the aha moment that, oh, wait, the eigenvalue is bounded, but the singular value is not. So let's just switch to that domain. And they really helped take that idea all the way to the theory that you saw earlier. Okay, so with that, let me just conclude by summarizing what I shared with you, which is this idea that if you're working in the very sparse regime where the SVD breaks down, the reason the SVD breaks down and gives localized singular vectors is because some of those rows and columns that have particularly large revealed entries end up dominating the computation. There are methods out there which are local, so to speak, that do recover the SVD or an estimate of the submatrix by doing some kind of clever thresholding, basically by filtering out high degree rows or columns and then computing the spectrum on the rest of the matrix. That's not what we're interested in doing. We're interested in sort of non-thresholding based global methods that just work right out of the box without any clever construction of which rows or columns to take. And if you do that, the key object that comes out is this asymmetric SVD, this randomized asymmetric SVD, which really works by taking advantage of the fact that the singular value of the perturbation matrix is blowing up, but the spectral radius of the masked version of that matrix ends up being bounded. And if you just convert the domain into complex domain, or you embed the matrix in complex domain, then all of a sudden you're able to find information and have the SVD salvage the matrix completion problem in a regime where folks maybe thought it was not. Okay, so let me conclude with that. And if you have any questions, I can answer them now. Maybe after Emily or Dustin turn off the video recording.
Right. Thank you for that nice talk. I encourage everyone to smash that reaction button.